Okay, right. So let's see. Now it sounds like you're okay with when the first part is really just a matter of sort of working out a little bit of algebra, but writing this as a linear combination of those two. And you're okay with that? Maybe you want to.
I think I am, but like.
Okay, let's go. Yeah, sure. Let's go ahead and go.
It was weird that you had two.
Yeah. Well, let's just see what happens here. So I'm going to explicitly write my wish list. All right, my wish list is that 352 would be a linear combination of. I don't know what these numbers are, but that's what a linear combination looks like, right? The vectors are 1, 1, 0 and 0, 1, 1. Okay, well, I can make this true if I can make each of the coordinate equations work out. So let's look at sort of the first coordinate and the second coordinate, etc., independently. So the first one says that. Well, it says that 3 is equal to C1. Well, here, let me write that over here. That says that 3 is equal to C1. Handy. This second one says that 5 is equal to C1 plus C2. And then the third one says 2 is equal to C2. So I've got to now solve, in this resulting system here, I've got to solve for C1 and C2. Conveniently, they're right there. By the way, notice that when the values are 3 and 2 as they have to be, notice that equation works as well. Everybody wins, right? And so that's what those numbers are. Yeah. Okay. Now there's an analogous process that we go through for part B, or for part 2, I guess. For this part, I want to write 0. Whoops. Sorry. I want to write 0 as a linear combination of, okay, and now 3 vectors. And the 3 vectors are, okay, 1, 1, 0, 0, 1, 1. And negative 1, 0, 1. Okay. Okay. Well, let's see here. And I'm going to get that a little bit more over that way. Okay. This first coordinate I can view as saying C1 minus C3 is equal to 0. So C1 and C3 are equal. The second coordinate I can view as saying C1 plus C2 is equal to 0. And the last one says that C2 plus C3 is equal to 0. Okay. So C1 and C, let's see how to write this down. C1 and C2 are negatives of each other. Yeah. C2 and C3 are negatives of each other. Well, they better be, because C1 and C3 we already knew were equal. That means that if C1 was the negative of C2, then C3 is also going to be the negative. Anyway, so those are the relationships, and there's actually a bunch of different solutions here. As long as I pick C1, C2, and C3 such that they satisfy these various relations that I have there, and I can do that by whatever I call C1. I have to call C3 the same thing, and then C2 has got to be the negative of that. So this is, anything of this sort is going to work. Does that make sense?
Yeah.
Okay. Yeah. Let's see here. Okay. Well, all right. I got ahead of myself here. I left the K. Okay, fine. So I'll tell you what. Let me just. All this part of the question said it was to find a way. So let me just say 1, negative 1, 1. How about that? Yeah. And just so that's because that's a way to do this. Okay. 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 1, -1, 1. Got to remember that. 1, -1, 1. Okay. Alrighty. Alright, so now are you comfortable with that statement? I mean, x is equal to itself plus 0, and I'm writing 0 as k times 0. Yeah?
Yeah.
Okay. All right. Well, I know from part 2. No, sorry, from part 1. I know that I can rewrite this x as let's see, what was it? 3u. Yeah, I'll do like this. 3u plus 2v. Right? Okay. Now, I also know from part 2 that I can write 0 as I gotta remember those numbers now. I think it was 1u minus 1v plus 1p. Pretty sure those were the numbers. Yeah. Well, what I've got then is a great big linear combination then of u, v, and p. All right, so if I just take all that and sort of multiply it out, then what I get is that x is equal to, well, there's 3 u's, but there's also k times 1 u's right there. So altogether, I have 3 plus k u's. And then now let's count v's. Well, I have 2v. Then I also have k times minus 1 v. So that's 2 minus k v's. And then let's count out p's. Okay, well, there aren't any p's on the... There's no p's over here. But I have k times 1 p's there. So plus k p. And that, as requested, that's an infinite number of different ways to write x as a linear combination of those vectors.
Okay.
Yeah. So roughly speaking, where the infinite comes from is from the fact that I found a way to do 0. And 0 is free. Right? It's nothing. I can add in 0 as many times as I like, and I'm not doing anything. So that's really kind of the weird thing about this business, about 0 equaling that, is that I've got what looks like a non-zero way to make 0 show up.
Mm-hmm.
And so this is a non-trivial linear combination that, even though it looks non-trivial, it's actually 0. And so that's what makes the infinite number of different possible ways of doing this possible. Yeah. Everybody happy with this one?
That's fine.
Okay. Cool. All right, hang on just 1 second. Let me stop this.